Okay, so today I want to continue talking about this Monte Carlo circle of ideas, and today we're going to talk about the Metropolis algorithm after we finish up the loose ends from last time. So the general heading for what we're doing now is putting Markov chains to work, and essentially Monte Carlo ideas are what we're talking about here. And we talked about the strong law of large numbers and the rate of convergence and all that sort of thing. And I went through a couple of examples, like if you want to compute the integral of some complicated function g on 0 to 1, you can sample uniform random variables, plug them in, take the average, blah, blah, blah. Convergence is probability 1 to the integral of g. Even if you can't compute that integral in closed form, we did that. We talked about computing the area of an awkward region, two-dimensional region, by surrounding it by a box, a square, and sampling uniform in there, and the percentage of samples that are in that box that come into the awkward region times the area of the big box is going to be the area of the awkward region. And at the very end of class last time, I was talking about two different ways to address a third problem. So we were talking about this problem. You're given some probability density. Let's call it P on the interval 0, 1. And what you want to do is you want to compute what I called EP of f, which is the integral from 0 to 1, f of x, p of x, dx, for some function f that's defined on 0 to 1 and real valued. Okay. And it occurred to me, there was a little mistake on the board that Rishi pointed out to me after class, which I'm going to correct a little later on, but it occurred to me that, there's no random variables here yet that I talked about. And so let me just phrase it in a slightly different way. Here's the idea. The idea is that if, say, capital X is a random variable with probability distribution, and actually let me use y here, with probability density p, so y is a random variable with probability density p, then what we're doing, the thing I call EP of f above, is really just the expected value of f of y. That's all it is. Okay? So if you want to think of it in terms of random variables and stuff, that's one way to think of it. But anyway, we had two methods for doing this. Method 1 was pick x1, x2, and so on, IID uniform on 0 to 1, and let z equal, say, f of x times p of x, or I'm just going to call that g of x, and compute g bar, the integral of g of x dx, e of g of x, which turns out to be EPF, okay, using this kind of thing here. Limit as n goes to infinity, 1 over n, sum from m equals 1 to n of g of xm equals that thing, EP of f, with probability 1 by the strong law of large numbers. So that's method 1. And method 2 was, instead of picking x1, x2, ID uniform of 0, 1, if you could somehow, I'll put that in big old quotes because we're going to talk about how we do that. Somehow, what we do is we pick, say, y1, y2, and so on, IID, distributed according to P. Okay, so these are going to be random variables with common density p, independent of each other. Then what I can do is I can let z, the new z, equal just f of y, and again by the strong law of large numbers, I can compute EP of f by means of the following, that the limit as n goes to infinity of 1 over n times the sum from n equals 1 to n of these f of y n is equal to EP of f with probability 1. Okay, so what I'm doing, I'm using the strong law of large numbers in both cases, and we did this all last time. If you weren't here last time and it looks crazy to you, then it's probably because you weren't here last time. But you might have watched the video in the meantime, whatever. But the point is, these are two methods that work equally well in some sense to find EP of f, but they're not really equal. Because if we look at the variance of the estimate, we saw last time that the thing that determines the speed of convergence I'll state it this way, is reflected in the variance of the estimate, the nth approximation about its mean, and that turns out to be, as we saw last time, whichever method you're using, whatever z you choose, it's going to be variance of z divided by n. And the variance of z for method 1 turns out to be integral from 0 to 1 f of x squared times p of x squared dx. And for method 2, the variance of z turns out to be integral from 0 to 1 f squared of x times just plain p of x, not p of x squared dx. So the difference here is in the p and the p squared. And the mistake I had on the board last time, I'll put it over here in, this is, if we go by the International Dateline Prime Meridian, I'm thinking this is like Belarus or something over here, or Sochi, or, whatever slightly Eastern blocky thing is on your mind right now. But the mistake I had on the board last time was for method 2, we're thinking of this, what did I have? I had g of, we had an incorrect formula for z. Okay, z here in method 2 is going to be f of y, okay, where y is distributed according to p. And yeah, so did you write it down, Rishi, by any chance? The incorrect thing we had on the board that you pointed out to me?
Yeah, you wrote g of x.
For z, for method 2? Or for method 1, had an incorrect, sorry, it was for method 1. I had an incorrect formula for z. I wrote z is equal to g of x f of x. So that's wrong. And the correct is z is equal to f of x p of x. So that's the right formula. So for those of you who are watching at home, you want to go back and edit the CD-ROM if you can, whatever. You can fix that for me. Make it look as if it never happened. I'd appreciate it. OK. So anyway, this is where we're at. This is correct. These were on the board correctly last time. What's the difference between these two things? The difference between the two variances for method 1 minus the one for method 2 is going to be so method 1 variance minus method 2 variance equals integral from 0 to 1 f squared of x times this thing p of x times p of x minus 1 dx. Now, I want to consider a situation where p is spiky. It's not uniform at all. So suppose, for example, p is quote-unquote spiky. And I'm not really sure whether to put an e between the k and the y in spiky. Should I? Like flaky, you take the e out, right? So what do you think? No e. OK. So here's an example of such a p. It could have, here's one out here. It has two tall sort of rectangular peaks like so, right? And each of them is of width little a, where a is small. And it's going to have height 1 over 2a, because it has to integrate to 1, like that. So suppose p of x looks like this versus x. OK? What is p of x times p of x minus 1 going to look like? Whose? What is it? What ringtone is it? You don't know. Then it turns out that p of x times p of x minus 1, it's equal to 0 most places. And it's equal to 1 over 2a times 1 over 2a minus 1, where those spikes occur. And when I integrate that times f, if a is small, then the difference of the variances is roughly equal to the square of the value of f at the location of this peak. So f squared of left peak, whatever that is, times 1 over 2a times 1 over 2a minus 1. I have to multiply that by a, so it's going to be 1/2 times 1 over 2a minus 1, plus f squared of right peak times 1/2 times 1 over 2a minus 1. And once again, the a disappeared because when I integrated, I multiplied by the width of the spike. And so you can see this goes like 1 over a. So the smaller a is, the bigger the difference between the variances of those two methods. And you can make that difference arbitrarily large by choosing a arbitrarily small. So what is the moral of the story? The moral of the story is, first off, it makes a difference which method you use. Okay. And in fact, in general, if we can figure out a way to draw samples as in method 2, quote unquote, sample according to a given p, comma, we might do a lot better, I'll get to you in a second, than if all we're allowed to do is take uniform samples. So if we can generate only uniform samples, we might get stuck with a huge variance in our estimate. And second of all, this better can be a lot better. And it's especially a lot better when the p according to which you're sampling is especially spiky. So the difference, the quote-unquote better in item 1 is especially pronounced when the P in question is spiky. And I've only given you a thumbnail justification for that using one simple example, but it turns out you can put some meat on this, some rigor. Intuitively, what's going on is you're wasting a lot of samples when you're not sampling where the action is taking place in F. First, I have to answer Mohammed's question. Yes?
So isn't it 1 over 2 A times 1 over 2 A? Yeah.
Okay, this disappeared, the A disappeared because when I integrate, what I have to do is multiply by the width of the pulses, and that cancels one of the A's. Got it? Rahul? Same question? Okay. Great minds think alike and equally... No, I'm just kidding.
And also, what if P is not spiky? What if it's something else?
If P is uniform, there's no difference between these two methods.
But if P is not uniform, then two methods are different.
Well, they're always going to be different when P is not uniform. They're always going to give a different result in terms of the variance of the estimate, the var of z, which is the numerator factor in the rate of convergence formula thing.
Then which one would be more accurate or...
It's generally better, it's almost always better to sample according to the P than to sample uniformly and use method 1. Okay. I'm trying to sell you the moral here. This is the whole sales pitch for the Metropolis algorithm. That you're given a P and you want to generate a bunch of samples distributed as according to P rather than uniform. Okay, and I'm trying to first, this is like the preliminary sales pitch. This is the vacuum cleaner salesman on the phone before he comes to your house. Okay, when I was a kid, there were actual vacuum cleaner salespeople who walked around, they went from house to house and they knocked on your door, cold calling, whatever. Yes?
So what does this intuitively, would it tell us that, I don't understand what the moral is, which is better when?
The two methods, the differences between the two methods. In one method, we were only able to sample uniformly on the unit interval, and we plugged those uniform samples into this composite function f times p. We averaged that over time. It did converge to the thing we wanted to. The rate of convergence was governed by 1 over square root of n that you can't do anything about, but also by the variance of that, which is that top formula there.
Right.
Same thing for method 2, except we were able to sample according to the distribution P. Like where P is high, we'll have a lot of samples. Where P is low, we'll have fewer samples.
Right.
And then and then what we do is we average F of those samples rather than F times P of those samples.
Right.
And then we get the same limit as we did before, same denominator, square root of n, whatever, but the variance is that second formula. And so what I'm doing over here is computing the difference between those two variances and showing that it's really big and positive in favor of method 2 when you have a spiky P. And therefore, the moral is that if we do method 2, in which we're able to sample according to P, then we'll do better. And in fact, you do especially better when you have a very spiky P, very non-uniform P. Rishi?
But we don't always know the distribution P beforehand.
No, we don't know the distribution, but we may know it according to a proportionality constant, and that's what I'm going to get to next when we talk about Metropolis. You'll see that. Yes?
So do we always use the second method and the first one?
Yeah.
Then is the first method important at all?
Well, it's the most if I'm going to tell you about Monte Carlo, and I'm telling you about approximating integrals, say, I got to start small. I got to start somewhere. I got to start with something we know that computers are good at.
No.
Computers are good at choosing uniform samples. A priori, we have no way of knowing how we're going to choose samples according to a given P. Maybe one of you out there knows. I certainly don't know. I will know by the end of this class, though, and so will you. Okay? All right. So hold all these thoughts. These are excellent questions, whatever. Let's go back to Los Alamos. Okay. These guys were interested in using computers to address problems in statistical mechanics. Okay, so folks there wanted to somehow apply these sort of random type techniques, Monte Carlo type techniques, to problems in statistical mechanics. Now, how many people here have had a course in statistical mechanics? Where? At your undergrad? Yeah. Well, good for you. That's good. My brother was an AP major at Cornell when it was just called EP. It was just called engineering physics. And he had to take a statistical mechanics course. And he came home, like I forget when it was, some school break, and he brought his textbook with him, right? And it was almost new at the time, but since then it's become a classic. Okay. And here's my copy of it in Dover paperback. Now, why did I bring this with me? Well, statistical mechanics is hard. Okay, and he showed me. He said, "You got to look at this. You got to look at this." Page 1, chapter 1. Okay, let me read this to you very quickly. No, it'll only take a sec. Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest, carrying on the work, died similarly in 1933. Now it is our turn to study statistical mechanics. Perhaps it will be wise to approach the subject cautiously. Okay, now this guy clearly has a sense of humor. He's a professor at Caltech. He's one of those academics whose career has sort of morphed into more of a book writing, teaching career than a rock star researcher career. He's well known in this community as writing excellent books and whatever, and I saw that. I thought it was so funny. You know, I don't know. Anyway, so that's statistical mechanics is hard. Okay, that's what you're supposed to get out of that. Okay, so what is statistical mechanics? What is it about? What is sort of the underlying picture in statistical mechanics? Suppose you have a system of many particles. Say a box full of gas, right? Okay, just untied my shoe, so to take a little break down here. Okay. So now it is our turn to study statistical mechanics. Okay, so here's the background picture. You have a system of many, say, molecules. For example, a mole of gas in some box. Okay. Now, what if you think of this as a mechanical system? Like along the lines of Newton, say, right? With a bunch of little point masses, right? And you try to analyze the dynamics of that system using Newton's laws. Okay, so if we regard this as sort of a Newtonian mechanical system of point masses, then there are an impossibly, well, there's uncountably infinitely many of them, but there's an impossibly high dimensional space of possible configurations that this can be in. Okay, so how big is that dimensional space, say, for a mole of gas? If every point mass has a position, which is 3 real variables, right? So with a position vector and a velocity or momentum vector, say, so let's use momentum vector for each of these particles, How big a space, how big a dimensional space are you dealing with on the order of?
How discrete can the points be?
Well, we're not going to discretize just yet. Okay, we're thinking of it as a true Newtonian mechanical system where the positions take on continuous values, maybe between some upper and lower bounds in each direction, if you're in a box. The velocities take on any continuous value up to perhaps the speed of light if we want to, pose relativistic constraints. So we're talking about some big r to the something. What is the something going to be? Well, you've got 6 numbers for each of those guys, so it's going to be 36 and change times 10 to the 23. So what we're dealing with here is we're dealing with an impossibly high dimensional space. So the system's state vector, and I'll put that phrase in quotes, is roughly 36 times 10 to the 23rd dimensional. Okay, so even today, even in the day of supercomputers, there's no way you can do some kind of a Newtonian mechanical analysis of a system whose state space is that high dimensional. Yes?
How do you get 6 dimensions?
3 position variables, 3 momentum variables for each, if you think of them. Got it? Okay. All right, so it's hopeless. It's hopeless to do a Newtonian sort of analysis of this. So, thus, a full Newtonian analysis is hopeless. Well, not that the analysis is hopeless, but doing it is hopeless. You can never do that. And by the way, this sort of puts the lie to a famous quote from Laplace. I don't know if you've ever heard this, but Laplace, after getting to understand Newtonian mechanics, said, if you told me the position and the velocity of every particle in the universe today, I could figure out the entire future of the universe and the entire past of the universe just by plugging them into Newton's laws. Well, there's you can see that just for 1 mole of gas, you can't even do that, much less the number of atoms in the universe. So Laplace was very optimistic, very overly optimistic there, in my humble opinion. Anyway, so the full Newtonian analysis is hopeless. Okay. All right, but the thing is, you could still think of the big space of possible positions and velocities of all these particles as a space, and as in a particular assignment of values to all those things, positions and velocities for each of the molecules, as being a configuration of the system. Okay, so you can still think of the state space. And this is called, people call it the phase space. Of such a system as being the set of all possible configurations of the system. Okay, and certainly some configurations are going to be more likely than others to occur, right? So some configurations, and this is sort of intuitive, are more likely than others. And I'll put the word likely in quotes because here's where we sneak in the probability. If someone comes up to you on Ho Plaza with a box full of a mole of gas, right, and says, I want you to guess, I want you to give me, hazard a guess, okay, as to where all the molecules in the gas are right now, how they're distributed in the box. It is theoretically possible for all of them to be like on the south side of the box, say the person's holding it north-south orientation, and there to be a complete vacuum, a lack of particles, right, on the north side of the box. That is theoretically possible. That is a possible configuration of the atoms. You're not going to guess that, right? You're going to guess that things are spread out, right? And the velocity distribution, like all the particles like in the middle, say, of the box could be standing still, and the other ones could be going around really fast. No, you're not going to find it that way. They're all going to be kind of moving around at the same average speed, right? So intuitively, some configurations are more likely than others, and if that person, you know, who's presenting you this box threatened to do something to you if you got it wrong, you would not guess one of those outlier configurations. Rishi?
I was just going to ask, what happens if we get it wrong, like in all these hypotheticals?
After you give a wrong answer or right answer on Ho Plaza?
Yeah.
It depends. If it's one of those dueling demonstrations things, you know, you might have to get a use of university property form to present boxes of gases to people. I don't know, you know. Right. Yeah, or they give you a sequence of samples and say, what signal did these come from? You know, you have to ask additional questions, right? Right, okay. These are all 3250 jokes for those of you who weren't privileged. Okay, so anyway, so Boltzmann, the first unfortunate suicidal statistical mechanician, Boltzmann thought, okay, well, you know, in the world, we tend to find things in configurations of the lowest energy, you know, that they sort of settle down, okay? So associated with some configuration, call it X, is some energy, which I'm going to call script E of X. And it could be like the total of the kinetic energy plus whatever other kinds of energies are pulling between things, however they're oriented, whatever. And physical systems tend to be, quote unquote, found in states of low energy. And if we go back to, remember we talked about protein formation, we talked about how you get the recipe through the ribosome and all these amino acid things come together and then they fold into a tertiary structure. That tertiary structure is essentially achieving a configuration of low energy. That's what goes on there, essentially. All right. So Boltzmann proposed the following probabilistic model that if you pick a random Ho Plaza presented system, whatever, then the probability density over phase space is going to have the following functional form. So the probability density over phase space, which is just this big, huge X space, takes the form P of X is proportional to, and so I'm going to say it's equal to C0, where C0 is some constant, times e to the minus E of X, the energy, divided by K times T, where C0 is a normalization constant. So what?
You said a nano-fab prelim. Same equation.
Really?
Yeah.
Who's teaching that?
Con.
Oh, right, the elevator guy, right? Actually, I saw him at the gym that day, you know, and he said, hey, Dave, how you doing? And I said, hey, and I kind of nudged him on the shoulder. Here, you got caught in an elevator today. He said, yes, and I called my student on the phone, and you know. Okay, and by the way, okay, while we have this little pause here, my friend Adam Roble from ECE, I saw him at the gym yesterday. And so I'm lying on the mat about to do some crunches, and he lies down on the mat next to me, and he says, warning, your class is going to ask you to move your prelim. And I said, why? We had that date first. And he said it's too close to DSP and to something else. MEMS, right.
When's the other DSP?
Tuesday the 25th of March is the day that I said I was going to try to have it.
When's the other DSP?
Okay, so you guys don't, okay, so Adam was wrong. Good. Good. Okay. No. C0 is a normalization constant, and K is what people call Boltzmann constant. See, I'm trying to lighten the mood here because we're studying statistical mechanics, which is dangerous. Okay, okay, so K is Boltzmann's constant, and T is absolute temperature. Okay. So let's look at that functional form. Now, he had no reason other than brilliance to come up with that. There was no experimental thing he could run at that time to give him this idea. This is just a pure, out-of-the-blue thought that he had to come up with this probability distribution. And if you look at it, you'll see that if E is low, then P takes on a relatively high values to when E is high. So this probability density is going to allot less mass to the high energy states than to the low energy states. So high E of x implies that P of x is small, and low E of x implies that P of x is large. So that fits, and why it takes on that functional form, that's just Boltzmann's brilliance to come up with that. Okay. Now, phase space, remember how high dimensional space is. And that thing, it turns out that there are relatively few like low energy configurations versus high ones. And so this is going to be very spiky in general. So this P of x, this thing P of x, which is called either the Boltzmann distribution, or another name for it is the canonical ensemble. And how did this come up in your nano course?
It's the rate constant proportional to exactly that. Or something like that. Of like a given chemical reaction.
Okay.
Band gaps.
Yeah, and just the
I forget what they are.
distribution in general.
Band gaps is the energy between like hydrogen. When you have hydrogen, you don't move up.
Oh, yeah, right.
Everything is proportional to e to the negative x.
E to the negative something over kt. Yeah, you know, you can't go wrong with that.
Yeah, isn't that like normal distributions, like some constants in that exponent?
And that, well, you know, and E of x goes like x squared, so that's like normal, you know, whatever. Anyway, so it's the Boltzmann, this P of x is very spiky. Okay, now what do people want to do with physical systems? What kind of questions is that person on Hope Plaza going to ask you? They're going to ask you, what do you think the value of the following quantity of interest is? Okay. So in statistical mechanics, you're interested in evaluating, and let's be really specific and call this P of x P beta for Boltzmann. Okay, so this is P beta. So in system mechanics, you're interested in calculating E sub P beta of F for various physical quantities of interest F defined on phase space. So F is a mapping from phase space to the reals.
E is expected, right?
E is always, in this course, a non-curly E is always expected value. Okay, now why is that hard? Why is that hard? Well, first of all, you don't even know this normalization constant C0. You only know like the functional form of the Boltzmann distribution. And to figure out C0, you would really have to integrate this over a 36 times 10 to the 23rd dimensional space. This horribly spiky thing. Impossible. Okay, so this is tough because you don't even know the normalization constant. And this addresses someone's question. Rishi, was it you? You might not know the distribution ahead of time. Sometimes you only know up to a constant. You only know the functional form of it. This is an example of that. Okay, so this is hard because this is obviously hard. You don't know C0, and furthermore, the integral is impossibly big and complicated. So what do we do in a situation like this? We say, okay, well, let's see if we can figure out a way to do this that doesn't entail figuring out C0, doesn't entail doing an integral. Let's use these Monte Carlo methods somehow. Let's figure out a clever way to do this. And that's where the Metropolis algorithm came from. Okay. Now, what does that algorithm do? So here's a solution. I'll put it in quotes, solution, because we don't know how to do this yet. Suppose that we could generate a bunch of independent samples from P, according to P. So generate somehow a sequence of samples, y1, y2, ... distributed IID according to P beta. Then what we could do is we could approximate along the lines of method 2 that we were talking about earlier. We can approximate E P beta of F by means of taking something like this, sum from m equals 1 to n, f of ym, something like that. And that is what the Metropolis algorithm is going to do in one form or another, as we'll see shortly. Okay? So this is the goal of the Metropolis algorithm. And so this is the setting. And the goal because setting and goal take different prepositions, the Metropolis algorithm. And the Metropolis algorithm got named just after Metropolis, and there's a lot of there's a lot of history type things you can read. I put some of them on the website. 50 years after the Metropolis algorithm, where are we now in computational science, whatever. But Andrew, you do.
I just had a question.
Sure, go ahead.
So, what would be like y1 and y2 in terms of the like particle and the mole and box example?
They would just be sample configurations that were distributed according to the Boltzmann ensemble. So if you actually evaluated these, if you think of them, you can think of them as either random variables or as a sequence of samples of IID, one IID random variable distributed according to P. So a given sequence of values of these is going to be like a bunch of configurations, right? And you're going to see more configurations with low energy than high energy, that kind of thing.
Oh, so it's like as if you could take a picture of the box, the entire box, and know what energy it's at.
Oh, well, I'm assuming as usual that it's fairly easy to plug in. Well, later. No, these are configurations. Yeah, a picture and a measurement of all the momenta. It's a big list of numbers. Each y is a big list of numbers, And it's going to, y1 is going to be one possible configuration when it's evaluated. Y2 is going to be another possible configuration, and so on. And you're going to see relatively few times a configuration that has a high energy and relatively more times a configuration that has a low energy. Like, you'll never see a configuration that has all the molecules on one side of the box and a vacuum on the other side. That's never going to happen. Or it happens with a very tiny probability, because E is huge in that case. They really wanted to fuse. I don't know.
And so then F of Y of M is just the energy associated with the configuration.
F is going to be any old physical quantity of interest whose average value over all possible configurations, average meaning expected with respect to P beta, you want to compute. Like, what is the, you know, say you had a physical quantity of interest. Let's call it, you know, I'm just going to make up a word. Ergonicity, okay? So I want to figure out the ergonicity, like if someone comes up to me on Hope Plaza with a box of gas and says, what ergonicity do you think this box of gas has? Well, a good guess is going to be the expected value of ergonicity with respect to the Boltzmann distribution, because I don't know how the velocities and positions in that particular box are arrayed. But if I think of them as distributed according to Boltzmann, then the expected value of a function with respect to that distribution, in this case the ergonicity, is going to be the value I guess. And so I say, okay, I know how to figure out the ergonicity for any particular configuration. I can just plug in all the different 10 to the 36 value, or 10 to the 23rd values and figure out what that ergonicity is for any given configuration. But it's very hard for me to integrate with respect to P beta because it's a hard integral. I don't even know the normalization constant or whatever. So what I want to do is I want to approximate that. And so what I'm going to do is I'm going to pull a bunch of sample configurations distributed according to P beta. And that's just a mathematical exercise I could do offline. And I'm going to plug them into the ergonicity, average them out, and lo and behold, this will converge as n goes to infinity to E P beta of F with probability 1. So F is any old function. It's not energy. It could be energy, but it's not necessarily. It's any old function on phase space. Every phase space configuration has associated with it certain values of quantities of interest, and you're trying to figure out their average with respect to this Boltzmann. Okay, so this is the setting and the goal of the Metropolis algorithm. And first what I'm going to do is describe the algorithm to you, and then I'm going to prove why it works. Okay. And just it's a good time to take the 3-minute breakdown, but I want to do another little show and tell because here's the paper that it came out in 1953. This is the paper, the original paper. And the authors, the list of authors, were Metropolis and Marshall Rosenbluth and his wife Ariana Rosenbluth, and Edward Teller and his wife Augusta Teller. Okay, so some cool things about this. Now, Edward Teller, he was the father of the hydrogen bomb. He was like the anti-Hans Bethe. You know, they were both at Los Alamos, and they sort of had a lifelong feud, and they competed to outlive each other. Hans won. Okay, anyway. And of course, there's legends about Teller. He was a great piano player, a very sensitive guy. Yeah, right, okay, whatever. But the cool thing is their wives participated in writing this paper, and this paper is known as anybody's top 20 list of papers in the history of computational science. This paper will be featured prominently. Okay, I guarantee it. And you know, the language is all statistical mechanics. You know, it's very physicsy and very hand wavy in terms of mathematics, but it's so cool. You know, like can you see this picture up here? This is like discretizing phase space. Can you see little spheres?
Yeah.
Yeah. Whatever. Okay. Well, anyway, let's take the 3-minute break, and then I'll describe the algorithm, and then probably next time explain mathematically why it works. All right. Well, I hope these guys won't be mad at me for starting again, but all right. So here's the deal. Here's how the Metropolis algorithm works, or what it does. And remember what its goal is. Its goal essentially is to generate a set of points in configuration space that are distributed according to the Boltzmann distribution. So the broad goal is to generate a set, and I'm going to call it script P, and that's going to suggest population or points or whatever. A set P of and in fact it's going to be a multi-set because there's going to be a possibility of repetitions here. Are you going to eat those pretzels in class, Will?
No, unless you want to.
No, okay. I was just asking. I know it sounded confrontational, but
I don't have to eat them.
no. I just had sushi with the faculty candidate who uses evolutionary game theory in her research. That was cool. Yeah. Okay. I didn't have time to get my cappuccino at Stella's, so I'm about to fall asleep. Anyway, so you want to generate a multi-set P of points in phase space, and you want this set to be distributed according to P, whatever that means. P beta. So that's the broad goal. So how are we going to do that? How do Metropolis and company do this? First, what you do is, and you're going to have to bear with me and take my word that you can sort of do this. It sounds hard, it sounds impossible, whatever. You settle on a fixed discretization of phase space. Don't ask me how. Don't ask me how they do this. And I'm going to call that set S. And that should suggest that this is going to be the state space of a Markov chain. And indeed, it's going to be. And I'm going to assume that S is finite here. But maybe huge. And of course, the fineness or whatever of the discretization that you could do nowadays with the computing power available today is much different from the fineness that you could deal with in 1951, 53, whatever. Okay, but you might say, well, where does this come from? If you have this 36 times 10 to the 23rd dimensional space, how do you discretize that? Well, you think of them as little cubes, that dimensional cube, phase space, and I don't know, whatever. And you could bound, say you had particles in a box, you could bound their positions by the dimensions of the box, you could bound their velocities or momenta 0 up to the speed of light, that kind of thing, whatever. All right, so anyway, you've got that. And you look at your Boltzmann distribution on phase space, and that induces, in some sense, so the Boltzmann distribution on phase space sort of induces on S a distribution on this discretization S. And I'm going to call it pi beta instead of p beta. And if you think of S as being since it's a countable set, you can put it in one-to-one correspondence with the positive integers, 1, 2, 3, ... up to some huge M. Okay. Then pi beta of J is going to be along the lines of, say, that normalization constant times e to the e of j, and I'll tell you what I mean by that over that in a second, where e of j is maybe, I'll put an approximation here, how about that? E of j is like the average energy of all the configurations in the phase space blob that corresponds with J in the state space S. Okay, so the way that or even minus, there's a minus sign there. Don't forget, it's always minus E over KT. So now you have this probability distribution over S that arises from the Boltzmann. Okay, now what you're going to try to do is you're going to try to generate a multiset of points from S, and I'm going to call that P. So you're going to generate P, which is a multiset of points from S as follows. And here's the algorithm. Here's how it works. It has two steps. Well, not counting initialization. So first, initialize it. By picking some arbitrary, and you know, you could do well by guessing well, but I'm just going to say pick some arbitrary point in S, and I'm going to call that point theta 0, and I'm going to put it into script P. So now, having initialized, I've got 1 point in P. So now P has 1 point in it. Okay, now I'm going to assume I have chosen theta 1, theta 2, theta 3, theta 4, etc. up through theta n, say, and put those all in P. And I want to tell you how to choose theta n plus 1. So, having chosen and put into P theta 1, theta 2, up through theta n, you choose theta n plus 1 as follows. And there's 2 steps to this procedure. 2 steps. One step is what we call the proposal step. So here's step 1. And I'll call this the proposal step. You start at theta n plus 1, and you flip a coin or whatever and perturb it in some uniform fashion to a nearest neighbor. Now, given the phase space is going to be like a big Euclidean space, and the discretization is going to be so that you have this notion of neighbor in the discretization. And you have this notion of what it means to perturb a uniform distance in terms of neighbors. So what you do is you start at theta sub n, and you choose what I'm going to call psi sub n plus 1 by perturbing uniformly, and I'm going to put an asterisk by uniformly here and put a little more descriptive discussion somewhere else, off theta n. So what does this asterisk over by uniformly mean? The discretization is going to have a notion of nearest neighbors, and it's going to be like some big grid. So the discretization is like a big connected grid. The nearest neighbors notion makes sense. And how far out you want to perturb from theta sub n and pick over a neighborhood, the size of this uniform perturbation is a user choice. So how big a net you want to cast to capture your psi sub n plus 1. So how big a uniform pert you make is a user choice. And we'll talk about that later on, why you might want to choose it one way or another. And what's your instinct? Why might you want to perturb a small amount versus a large amount, or a large amount versus a small amount when you make this proposal? Matt?
Like quality versus speed.
Yeah, it's essentially like there's a lot of jargon that goes along with this in the optimization community. Have you ever heard of the exploitation versus exploration trade-off? No? Okay, well you will. Like if you perturb a small amount, you might get like stuck at a local min, you know, that kind of thing, right? When you're doing optimization. So this is a matter of step size in an optimization element. Okay. Anyway, that's the proposal step. Step 2. This is the accept, reject step. And any of us who's ever written a proposal to the National Science Foundation or any other funding agency knows what it means to have it rejected, what it means to have it accepted. I don't think anybody's got a perfect track record except maybe John Kleinberg. Who knows? I don't know. And he probably deserves it. Okay, here's the accept, reject step. How does this go? If the energy E of psi n plus 1 is less than or equal to E of psi n, or E of theta n. In other words, if your perturbation lands you in a configuration of equal or lower energy to the one in which you started, you accept psi n plus 1. That is to say, you set theta n plus 1 equal to psi n plus 1 and throw it into P and proceed. In other words, you go back up here to step 1. If, on the other hand, you perturb to a state of energy higher than the energy of the state you start with, what do you think you do? Well, Matt just wants to, he wants to do greedy hill climbing. That's what he wants to do. He wants to only accept things of higher energy.
Pick a different step size. Pick another thing, perturb somewhere else.
Drew?
Accept it with some probability and reject it with some of the opposite.
1 minus that? That's actually what you do. You make it possible to accept a lower energy state, and that enables you to explore further into the configuration space. Okay?
Simulated annealing.
Well, this is simulated annealing is doing this again and again and again at different temperatures. We'll see that when we talk about it.
All right.
Okay? So anyway, if E of j is bigger than E of I, then you accept with probability. And what is the probability going to be? It's going to be e to the minus, parentheses, E of I minus E of j, or E of j minus E of I over kt. That is to say, with that probability, you set theta n plus 1 equal to psi n plus 1 and throw it into your multiset P, and you reject with probability 1 minus that. Okay? And this is always less than 1, by the way, because E of j is assumed to be bigger than E of I, so the exponent is negative. You reject it with probability 1 minus that. What does rejection mean? That means that you set theta n plus 1 back equal to theta n, and you throw another copy of theta n into P. And then proceed. And of course, there's proceed after that. And we keep doing this again and again and again. And you can see that it's possible, like, we get stuck on one theta forever and keep throwing more and more copies of that in the bin. If we keep perturbing to a higher energy state and we keep flipping this coin and having it come up negative, we keep throwing more copies of theta n in, you know, whatever. Okay, so doing this, what you do is you generate a set of points in configuration space. And it turns out that they are arrayed, they're distributed according to the Boltzmann, the discretized version, pi beta of the Boltzmann ensemble, p beta. And that's the miracle of it. And I'm not going to have time to prove that today, but let me just tell you, first of all, p is the script p that you generate as above is distributed over this S according to pi beta, the discrete Boltzmann ensemble. I keep saying ensemble. That's like a synonym for distribution in this context. Okay? And we'll prove this. It's very easy, turns out. Furthermore, a bonus is that we've generated these things, the guys in P, recursively. Recursively. Computers love doing stuff like this. They love flipping a coin, checking something, accepting if so-and-so is true, doing another coin flip if so-and-so is false, accepting if something, you know, that kind of, they love doing stuff like that. Okay, so this is tailor-made for computer implementation. So this algorithm generates this set, P, recursively. Okay? And clearly it's computationally appealing, and we can make it run faster by making the step size smaller, making the uniform perturbation smaller. We can make it run slower and more carefully by making that big. You know, we can do all these different user choices in the algorithm to make it behave differently depending on what kind of computing power is available to us, blah, 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 blah. Go on and on like that. Okay. Now, also, and this is the way we're going to prove, number one, it turns out that doing this algorithm is running a Markov chain on S. So doing the algorithm is running a Markov chain just occurred to me, I said computers love doing things like that, but computers probably don't love anything. You know, I mean, if you, unless you're, you know, the Turing test, all that stuff. Has anyone seen the movie Her? Was it good? You thought it was good? Okay. I was thinking that would be a good one. I'm going to wait for it to come out on, you know, video or something. Right? It's not like Star Wars, you have to go see it, whatever. Okay, so anyway, the algorithm is running a Markov chain on S. And this Markov chain turns out to be irreducible and has unique stationary distribution. Guess what? Pi beta. And this is what we actually use to prove item 1. Okay. So we use this to prove 1, using all our limit theorems and stuff from Markov chains. And this is a great example of putting Markov chains to work. You've got a Markov chain, which is running a Markov chain is a naturally recursive kind of thing to do. by running some Markov chain, which is easy from a computational standpoint, you solve the difficult problem of generating a set of points in a big space that are distributed according to some probability distribution. And why you would ever want to do that, that was the sales pitch. That was the vacuum cleaner part of the lecture. Okay. So anyway, okay, so we'll pick that up next time. And